In December 2018, a spacecraft built in the early 1970s crossed a boundary that no human instrument had ever crossed from a second direction. Voyager 2, launched on August 20th, 1977, 16 days before its twin, Voyager 1, passed through the heliopause, the outermost boundary of the Sun's influence, and entered interstellar space. It was the second time in history that a human-made object had achieved this crossing. Voyager 1 had done it first, in August 2012, from a different location and on a different trajectory. 6 years separated the two events. The data they returned from those crossings, when placed side by side, produced something scientists had not fully anticipated. Not confirmation of the model they had built over decades, but a specific and pointed challenge to it. The heliopause had long been one of the most anticipated boundaries in space physics. A clean, theoretically well-defined line where the sun's reach ends and the galaxy's begins. What the Voyagers found instead was a boundary that behaves in ways the models did not predict, a transition zone that is sharper in some respects than expected and stranger in others, and a magnetic environment that has quietly unsettled a field of science that thought it knew what to expect. This is the story of what Voyager 2 found, how it differs from what Voyager 1 found, and what the comparison between the two crossings is telling us about the shape and nature of the bubble our solar system inhabits. Before we dive in, if you subscribe, the algorithm works in our favor. It costs you nothing and helps this content find the audience it deserves. Voyager 1 and Voyager 2 are often spoken of as a pair, and in origin they were. Nearly identical spacecraft built from the same design, launched within weeks of each other in the summer of 1977 to take advantage of a rare planetary alignment that occurs once every 175 years. With Jupiter, Saturn, Uranus, and Neptune arranged on the same side of the Sun, a single spacecraft could visit all four using gravity assists, each planet bending and accelerating the spacecraft's trajectory toward the next, with no additional fuel expenditure beyond what was needed for course corrections. The opportunity was too significant to use only once, so NASA sent two. But the twins quickly diverged. Voyager 1, despite launching second, was placed on a faster trajectory and overtook its twin within weeks. It made close flybys of Jupiter and Saturn, and at Saturn it was directed toward a close encounter with Titan, a scientific priority that bent its path sharply out of the plane of the solar system, ending its planetary tour, but accelerating it onto a trajectory heading roughly toward the nose of the heliosphere, the direction in which the Sun is moving through the galaxy. Voyager 2 took a different path. Its Saturn flyby was less steeply inclined, allowing it to continue onward to Uranus, which it reached in January 1986, and then to Neptune, which it flew past in August 1989. Voyager 2's Neptune flyby was one of the great single events in the history of planetary exploration. Neptune, the outermost planet, had never been visited. Its largest moon, Triton, a world now understood to be a captured Kuiper Belt object larger than Pluto, was photographed for the first time at close range, revealing a nitrogen ice surface with active geysers erupting dark plumes several kilometers into the thin atmosphere. Neptune itself turned out to host winds of up to 2,100 kilometers per hour, the fastest sustained winds in the solar system, and a storm system called the Great Dark Spot, analogous in structure to Jupiter's Great Red Spot, though unlike Jupiter's, Neptune's Great Dark Spot had disappeared by the time the Hubble Space Telescope looked for it a few years later. After Neptune, Voyager 2's planetary mission was complete. Like its twin, it was now simply moving outward, but on a trajectory headed toward the southern hemisphere of the heliosphere, roughly 60 degrees away from the direction Voyager 1 was traveling. The two spacecraft were, in effect, probing two different parts of the same boundary. The Sun does not merely radiate light and heat. It continuously exhales a stream of charged particles, electrons, protons, and helium nuclei, called the solar wind, traveling outward at speeds between 400 and 800 kilometers per second. This stream does not simply fade with distance. It pushes against the interstellar medium, the diffuse gas and magnetic field that fills the space between stars, and inflates a vast bubble called the heliosphere. The solar wind dominates the environment inside this bubble. The interstellar medium dominates everything outside it. The boundary between these two domains has a layered structure. The first layer, moving outward from the Sun, is the termination shock, the point where the solar wind, traveling supersonically outward, slows abruptly to subsonic speeds because it is running into the resistance of the interstellar medium. Voyager 1 crossed the termination shock in 2004 at approximately 94 astronomical units from the Sun. Voyager 2 crossed it in 2007 at approximately 84 astronomical units, notably closer, suggesting the heliosphere is not symmetrical and the boundary is closer to the Sun in the direction Voyager 2 was traveling. Beyond the termination shock lies the heliosheath, a thick region of compressed, turbulent, subsonic solar wind, piling up before it reaches the heliopause itself. The heliopause is the actual outer boundary, the surface where the solar wind's outward pressure finally balances the inward pressure of the interstellar medium, and beyond which solar wind particles cannot penetrate. Cross it, and you are in interstellar space, a domain governed by the galaxy, not the Sun. Before either Voyager crossed the heliopause, the theoretical picture of what the crossing should look like was relatively clear. Solar wind particles should drop sharply. Galactic cosmic rays, high-energy particles from outside the solar system that the heliosphere partially shields, should surge. The magnetic field should change direction. Inside the heliosphere, it reflects the Sun's extended magnetic influence. Outside, it should align with the interstellar field shaped by the broader galaxy. The transition might be somewhat diffuse, but the overall character of the change should be unambiguous. Scientists had been refining this picture for decades. They were confident in its broad outlines. When Voyager 1 crossed the heliopause in August 2012, the solar wind particle data behaved largely as predicted. The flux of solar wind particles dropped sharply, and galactic cosmic rays increased simultaneously. The plasma density, measured indirectly through plasma wave oscillations after Voyager 1's plasma science instrument failed in 1980, jumped by a factor of roughly 40 upon crossing, consistent with the transition from the tenuous solar wind to the denser interstellar plasma. These were confirmations of the model's basic structure. The magnetic field was another matter entirely. The models had predicted that crossing the heliopause would produce a clear change in the direction of the magnetic field, a rotation of roughly 40 degrees or more, reflecting the transition from the Sun-dominated heliospheric field to the galaxy-dominated interstellar field. What Voyager 1 measured was a change in field strength. It increased, but almost no change in direction. The field on both sides of the boundary was pointing in nearly the same direction. The discrepancy was not subtle. It was a central prediction of the model, and the model was wrong. Various explanations were proposed. Perhaps the local interstellar magnetic field happens, by coincidence, to be nearly parallel to the heliospheric field in the region Voyager 1 crossed. Perhaps the heliosphere drapes and realigns the surrounding interstellar field through a process called magnetic draping, pulling it into partial alignment with the solar field. Perhaps the model's estimates of the interstellar field direction were simply inaccurate, built from indirect remote sensing observations that lacked the precision of Voyager's in-situ measurements. None of these explanations was confirmed. The anomaly remained open. Scientists hoped that Voyager 2's crossing, approaching from a completely different direction, would help resolve the question. If the magnetic field alignment was a local coincidence specific to the region Voyager 1 crossed, Voyager 2 might see the expected directional shift from the opposite end of the heliosphere. 6 years later, it did not. Voyager 2 crossed the heliopause in December 2018 at a distance of approximately 119 astronomical units from the Sun, slightly closer than Voyager 1's crossing at approximately 121 astronomical units, but in a completely different direction, roughly toward the southern galactic hemisphere. 5 papers published simultaneously in Nature Astronomy in November 2019 reported the findings in detail and the picture they presented was both confirming and newly perplexing. The basic transition was clear. Voyager 2's low-energy charged particle instrument recorded an abrupt drop in heliospheric particles. Its cosmic ray subsystem recorded a simultaneous increase in galactic cosmic rays. Its plasma science instrument, which, unlike Voyager 1's, was still functioning, directly measured the plasma environment on both sides of the boundary, confirming the density jump from heliospheric to interstellar plasma. On these fundamental counts, the heliopause was real and behaved broadly as the models described. But several specific measurements were surprising. The heliopause crossing, as measured by the plasma and particle instruments, was extremely sharp, occurring over a spatial scale of less than 1 astronomical unit, or less than 150 million kilometers. This was sharper than many models had predicted. Even more unexpected, Voyager 2 detected a layer of hot, compressed plasma just inside the heliopause, in the outer heliosheath, that had not been predicted by models and whose origin is not fully understood. This hot plasma layer, with temperatures of several 100,000 degrees Celsius, appears to be a feature of the heliospheric boundary region that existing theoretical frameworks had not accounted for. And then, again, the magnetic field. As with Voyager 1, the field strength increased upon crossing the heliopause, but the direction barely changed. The interstellar magnetic field measured by Voyager 2 in the southern heliosphere was pointing in a direction closely aligned with the field inside the heliosphere. The same anomaly that had puzzled scientists after Voyager 1's crossing appeared again, from the opposite end of the boundary. Two crossings, 6 years apart, from trajectories roughly 60 degrees apart in latitude, producing the same unexpected result. This was no longer a local coincidence. It was a systematic feature of the boundary. The scientific value of having two Voyager crossings is not simply that it doubles the data. It is that two crossings from different directions allow scientists to constrain the shape and properties of the heliosphere in ways that a single crossing cannot. Several important conclusions emerge from comparing the two datasets directly. First, the heliosphere is not symmetric. Voyager 1 crossed the termination shock at 94 astronomical units in the nose direction. Voyager 2 crossed it at 84 astronomical units, heading roughly southward. This 10 astronomical units difference in termination shock distance indicates that the heliosphere is compressed on its southern flank. The boundary is approximately 10% closer to the Sun in the direction Voyager 2 was traveling. This asymmetry was not present in pre-mission models, which generally assumed a broadly symmetric heliosphere. It implies that the interstellar medium is not applying equal pressure from all directions, which in turn tells us something about the distribution of interstellar material and magnetic field in the Sun's immediate cosmic neighborhood. Second, the heliopause appears to be an active, dynamic boundary rather than a passive membrane. Both Voyagers detected evidence of material mixing in the boundary region. Solar wind particles appearing briefly on the interstellar side of the heliopause, and interstellar particles appearing on the heliospheric side, suggesting the boundary is not perfectly impermeable. Reconnection events, magnetic field lines from the two domains linking and breaking, may be allowing material to cross in both directions, blurring the boundary at small scales, even as it remains well-defined at large scales. Third, and most significantly, the magnetic alignment anomaly is not a local effect. The interstellar magnetic field, as measured by both Voyagers, is closely aligned with the heliospheric magnetic field at both crossing locations, even though the two crossing points are separated by vast distances. The most widely accepted current interpretation is that the heliosphere itself has distorted and aligned the surrounding interstellar field through magnetic draping, the process by which a magnetized object moving through an external magnetic field drags field lines along with it, bending them into rough alignment with its own orientation. If this is correct, the heliosphere has been reshaping its magnetic neighborhood over geological time, and the region immediately surrounding our solar system reflects not the pristine interstellar field, but a field that has been modified by the sun's presence. Understanding where this region of modified field ends and the true undisturbed interstellar field begins requires observations from a third crossing point, a direction for which no mission currently exists. The Voyager crossings have become central evidence in a broader scientific debate about the overall shape of the heliosphere that has been ongoing since the mid-2000s. The traditional model, built over decades, depicted the heliosphere as a comet-shaped structure, roughly spherical at the front, where the sun is moving into the interstellar medium, and stretched into a long tail, the heliotail, at the rear, where the solar wind is pushed back by the relative motion of the sun through the galaxy. This picture was intuitive and consistent with the known physics of objects moving through external media. In 2015, a team led by researchers at the University of Alabama in Huntsville published an analysis of data from NASA's Interstellar Boundary Explorer satellite, known as IBEX, which maps the heliospheric boundary indirectly by detecting energetic neutral atoms produced at the boundary region. Their analysis suggested the heliosphere is not comet-shaped at all, but more crescent-shaped, compressed on the flanks by the interstellar magnetic field and lacking a significant tail. The driving argument was that the interstellar magnetic field Voyager measured, stronger than pre-mission models had assumed, exerts enough lateral pressure on the heliosphere to squeeze its flanks inward and suppress the formation of a long tail. This interpretation remains contested. A 2020 study using a different analysis of IBEX data and incorporating Voyager plasma measurements argued for a more intermediate shape, not the classic elongated comet, but not crescent-shaped either. Other modeling teams have produced heliospheres of varying shapes, depending on which boundary conditions and physical assumptions they use. The core problem is that we have only two in situ crossing points, both in the roughly noseward hemisphere of the heliosphere, and no direct measurements from the tail region, which is where the shape models diverge most significantly. Without a mission designed to cross the heliopause in the tail direction, the shape debate cannot be resolved from observation alone. What is not in dispute is that the heliosphere is smaller and more asymmetric than the pre-Voyager consensus assumed, and that the interstellar magnetic field it interacts with is stronger than expected. These two facts together mean that the sun's protective bubble is more tightly constrained by its galactic environment than the solar physics community had modeled. The implications extend beyond abstract heliospheric science. The heliosphere mediates the flux of galactic cosmic rays reaching the inner solar system, and any variations in its size and shape over geological timescales could affect the radiation environment experienced by Earth. Voyager 2 is currently more than 20 billion kilometers from Earth, moving at approximately 55,000 kilometers per hour. Its power comes from 3 radioisotope thermoelectric generators, converting the heat of decaying plutonium-238 into electricity. Each generator loses roughly 4 watts of power per year. By the mid-2020s, the combined output has fallen to approximately 230 watts, enough to power a modest string of light bulbs. NASA engineers have been methodically shutting down heaters and non-essential systems for years, routing the remaining power to the instruments most capable of returning useful science from interstellar space. In 2020, a software error caused Voyager 2 to briefly switch to a backup fault protection system that consumed too much power, forcing several instruments offline. The team at JPL spent weeks carefully cycling power to restore normal operations. All of this conducted at a signal round-trip time of over 34 hours, meaning each command and its response consumed more than a day and a half. The recovery was successful, and the plasma science instrument, Voyager 2's single most valuable asset in interstellar space, given that Voyager 1's equivalent failed in 1980, was restored to operation. That instrument alone justifies the extraordinary effort required to keep Voyager 2 functional. It is the only direct plasma measurement device currently operating in interstellar space, and it is returning data from a region that no other instrument in human history has sampled. The plasma science instrument's continued operation means Voyager 2 can do something Voyager 1 cannot: directly measure the density, temperature, and velocity of the interstellar plasma as the spacecraft moves deeper into the interstellar medium. These measurements are building a profile of the local interstellar environment over distance, the first such profile ever obtained. Each year of continued operation extends that profile further and allows scientists to test whether the properties of the interstellar medium are uniform or vary with position, a question with direct implications for understanding the Sun's galactic neighborhood. Voyager 2's heliopause crossing did not overturn the fundamental physics of the heliosphere. The heliosphere exists. The heliopause is real. Solar wind particles stop at the boundary, and galactic cosmic rays increase beyond it. The basic structure that solar physicists built over 60 years of theoretical and observational work is correct in its broad outlines. What Voyager 2 did, in combination with Voyager 1, is reveal that the details are significantly more complex than the models assumed, and that some of the most specific, testable predictions those models made were wrong. The magnetic field does not rotate as predicted at the crossing. The heliosphere is asymmetric in ways the pre-mission models did not capture. The boundary is sharper than many theorists expected, yet contains plasma structures, like the hot outer heliosheath layer Voyager 2 detected, that the models did not predict. The interstellar medium is denser and its magnetic field stronger than the values most models used. These are not minor corrections. They are the kind of discrepancies that require a generation of revised modeling to fully incorporate. There is a particular scientific significance to the fact that Voyager 2's plasma science instrument survived to make these measurements. Solar heliospheric physics has been built primarily on remote sensing, detecting energetic neutral atoms, observing radio emissions, inferring plasma conditions from indirect measurements. Voyager 2's in situ plasma data from interstellar space is the field's first ground truth. Not an inference, not a model output, but a direct measurement of the medium itself. Every model of the heliospheric boundary that has been built in the past century can now be tested against that data. Many have already been found wanting, and the process of revision is ongoing. Voyager 2 was designed for a 4-year planetary mission. It is now in its 5th decade of operation, transmitting from a region no mission was expected to reach, returning data from an environment no theoretical model had fully characterized, and producing results that are still reshaping a field of science. The boundary it crossed was supposed to be well understood. Instead, it turned out to be one of the most productively surprising places our machines have ever visited. A frontier that behaved strangely enough to prove that even the edge of our own solar system is not yet fully mapped. That is, by any measure, an extraordinary final chapter for a spacecraft that was never supposed to have one.